Hello dear students, in this video I'll start with the 8th unit, which is linear programming problem. Here we will see what is the meaning of mathematical formulation of a linear programming problem, or how to write the mathematical formulation of the given linear programming problem. I'll explain decision variable, subjective function and constraints with an example. So here is an example of a linear programming problem. A furniture manufacturer makes two products, chairs and tables. Processing of these products is done on two machines A and B. A chair requires 2 hours on machine A and 6 hours on machine B. A table requires 5 hours on machine A and no time on machine B. There are 16 hours per day available on machine A and 30 hours on machine B. Profit gained by the manufacturer for a chair and a table is ₹2 and ₹10 respectively. Formulate this problem as a linear programming problem to maximize the total profit of the manufacturer. So here we can see that a manufacturer makes two products, chairs and tables. So these are the two products which the manufacturer makes, chairs and tables. And the processing of these products, it is done on machines A and B. A chair requires 2 hours on machine A and 6 hours on machine B. And a table requires 5 hours on machine A and no time on machine B. And 16 hours are available on machine A and 30 hours are available on machine B in total. The profit for a chair and a table is also given. Now we need to formulate this problem to maximize the total profit of the manufacturer. So let us draw a table. So here we have the machines A and B and the products chair and table. Chair requires 2 hours on machine A and 6 hours on machine B. A table requires 5 hours on machine A alone and no time on machine B. The available time for machine A is 16 hours and available time for machine B is 30 hours. The profit per unit on chair is ₹2 and on table is ₹10. So here if we see this problem, now this problem has an objective. The objective or the aim is to maximize the total profit of the manufacturer. So we have to find the number of chairs and tables that the manufacturer should make so that the profit will be maximized. So that is the objective function, and finding the number of chairs and tables, it is nothing but it is the decision variable. So let us take, let x and y number of chairs and tables be produced respectively. So here x and y represent the decision variables. So we have x and y, the decision variables. And as I already mentioned, the objective of this is to maximize the profit. So the objective function is given by maximize. Usually the objective function is represented by z. Maximize z is equal to, we need to find the number of chairs and tables that has to be produced so that the profit will be maximized. So we need to maximize 2x plus 10y, because we have taken x as number of chairs and y as number of tables. So we have to maximize this function 2x plus 10y. Now to maximize z is equal to 2x plus 10y, we have some conditions which are given. These conditions are called the constraints. So we have a chair which requires 2 hours on machine A and 6 hours on machine B. A table which requires 5 hours on machine A and no time on machine B. The maximum available time on machine A, it is only 16 hours. So the condition for machine A is that machine A can operate only for 16 hours. So we have to maximize this subject to certain constraints. Subject to the constraints. 2x plus 5y. We have taken x as the number of chairs and y as the number of tables. So, the time on machine A, it is given by 2x plus 5y. Now, this total time should not exceed 16. So, 2x plus 5y less than or equal to 16. So, this is the first constraint. And then the second constraint is on the time available for machine B. The machine B available time is 30 hours and a chair requires 6 hours on machine B. So, we have 6x less than or equal to 30, or we have x less than or equal to 5. Now, this is the constraint on machine A and this is the constraint on machine B. And apart from that, we have got one more constraint. We have taken x and y as the number of chairs and tables to be produced. Now, this cannot be negative. A company or a manufacturer cannot produce negative number of chairs or tables. So, we have x greater than or equal to 0 and y greater than or equal to 0. These are the non-negative constraints. Now, why it is called non-negative? Because production of negative number of chairs and tables is not possible. So, that is the reason why we have the value of x should be greater than or equal to 0 and the value of y should also be greater than or equal to 0. So, this is the mathematical formulation of the given linear programming problem. So, the mathematical formulation is given by the objective function is maximize z is equal to 2x plus 10y subject to the constraints 2x plus 5y less than or equal to 16, 6x less than or equal to 30, that is x less than or equal to 5 and x greater than or equal to 0 and y greater than or equal to 0. So, this is the mathematical formulation of the given linear programming problem. So, the three things which I have seen here are, one is the decision variable. So, we have seen the decision variable, then the objective function, the constraints and the non-negative constraints. So, the three important things as far as a linear programming problem is concerned are decision variables, objective function and the linear constraints. Now, we have seen an example and understood these terms. Now, we will see the meaning in detail. Decision variable, it refers to the limitations or the activities that are competing with one another for sharing the available resources. So, in the example which we just now saw, we have chairs and tables which is competing for machines A and B. Now, we cannot say let the chairs be produced first and then let us produce tables, or let the tables be produced first and then the chairs. Here, we need to have a simultaneous solution because the utilization of resources are interrelated. So, this is with respect to decision variables. All the decision variables are considered to be continuous, controllable and non-negative and represented as variables x, y, etc. So, we usually deal with linear programming problem in two decision variables x and y. And then we have the objective function. Every linear programming problem is aimed to have an objective to be measured in quantitative terms. Now, this objective function, it can be either profit or sales maximization, or it can be cost or time minimization and so on. The next important assumption is the relationship among the variables representing objective, it must be linear and it is a real valued function represented as z is equal to ax plus by, where a and b are arbitrary constants and we have this z to be maximized or minimized. And then the third component is the constraints, the limitations on the use of resources. The resources are labor, space, availability of raw material or restriction of transportation, etc. All these are the limitations that are available in any problem. So these limitations, it will limit the extent to which an objective can be achieved. So those constraints are expressed as linear inequalities or equalities in terms of the decision variable. So they are usually expressed as linear inequalities or equalities of the decision variables x and y. And then we have the non-negative restrictions on the decision variables. So these are the important points regarding formulation of a linear programming problem. So we have the decision variables. First we have to decide what are the decision variables, and then we have to see what is the objective or the aim of the linear programming problem. Then we have to write the objective function, and then we have to see what are the various limitations or constraints or conditions that are given on the use of resources, and then we have to write the constraints. And now the different types of linear programming problems. There are various types of linear programming problems. They are manufacturing problem, diet problem, transportation problem, and assignment problem. The example which we just now saw, it is a manufacturing problem. Now as we solve the questions from the exercise, I will tell which is diet problem, which is transportation problem, and which is assignment problem. So as we see the question, it will be easy to understand each of these. Now moving on to the section 8.6, check your progress of CBSE Handbook, the student support material from Unit 8, linear programming problem. The first question: to maintain his health, a person must fulfill certain daily requirements for several kinds of nutrients. Assuming that there are only 3 kinds of nutrients, calcium, then protein and calories, and the person's diet consists of only 2 food items 1 and 2, whose price and nutrient contents are shown in the table below. So we have the various nutrients here, then we have the first food, the second food. So for every pound of each of these food, the requirement for calcium, protein and calories are given here. And the minimum daily requirement is also given for each of these nutrients. And then the price in rupees of each food, the first food and the second food, it is given here. Now we have the question: what combination of 2 food items will satisfy the daily requirement and entail the least cost? Formulate this problem as a linear programming problem. So here, to maintain health, so this is a diet problem. So to maintain a person's health, a person has to fulfill certain daily requirements. This is a diet problem. Now we need to find what combination of these 2 food items will satisfy the daily requirement and also entail the least cost. So we are assuming there are only the first food item and second food item which is given here, and there are only 3 nutrients: calcium, protein and calories. The price of each food is given here. Now let us formulate this. So let us take, let x and y represent the number of units of the first food and the second food respectively. So the objective is we have to minimize the total cost. So the objective function is given by minimize z is equal to 0.60x plus 1.00y. So we have to minimize the total cost subject to the constraints. Now what are the constraints? Now the first food has 10 units of calcium per pound and the second food has 4 units of calcium per pound. The minimum daily requirement is 20 units of calcium. So the first constraint with respect to the nutrient calcium is, it is 10x plus 4y greater than or equal to 20. Since here the minimum daily requirement is 20 units, this should be greater than or equal to 20. And then we have the next constraint with respect to protein. Here 1 pound of the first food has 5 units of protein and 1 pound of the second food has 5 units of protein. The minimum daily requirement for protein is 20 units. So the second constraint is 5x plus 5y greater than or equal to 20. And then we have the next constraint with respect to calories. The minimum daily requirement for calories is 13. The first food has 2 calories and the second food has 6 calories. So we have 2x plus 6y greater than or equal to 13. So this is the constraint with respect to calcium. Then this is a constraint with respect to protein. And this is the constraint with respect to calories. We need not write all these. I am just writing it for a better understanding. And then finally we have the non-negative constraints. X greater than or equal to 0 and y greater than or equal to 0. So the mathematical formulation of this given problem is given by the objective function minimize z is equal to 0.6x plus y subject to the constraints 10x plus 4y greater than or equal to 20, 5x plus 5y greater than or equal to 20, 2x plus 6y greater than or equal to 13, x greater than or equal to 0 and y greater than or equal to 0. Now moving on to the next question. Vitamins A and B are found in two different foods, F1 and F2. 1 unit of food F1 contains 2 units of vitamin A and 3 units of vitamin B. 1 unit of F2 contains 4 units of vitamin A and 2 units of vitamin B. 1 unit of F1 and F2 cost rupees 5 and rupees 2.5 respectively. The minimum daily requirements for a person of vitamin A and B are 40 and 50 units respectively. Assuming that anything in excess of daily minimum requirement of vitamin A and B is not harmful, find out the optimum mixture of food F1 and F2 at the minimum cost which meets the daily requirement of vitamin A and B. Formulate this problem as an LPP. So here we have two vitamins A and B which is found in two different foods F1 and F2. Now let us draw this table. We have two vitamins, vitamin A and vitamin B, and two foods F1 and F2. Now it is given 1 unit of food F1 contains 2 units of vitamin A and 3 units of vitamin B. So F1 contains 2 units of vitamin A and 3 units of vitamin B. And then 1 unit of F2 contains 4 units of vitamin A and 2 units of vitamin B. So F2 contains 4 units of vitamin A and 2 units of vitamin B. And then 1 unit of F1 cost rupees 5. So F1 cost rupees 5 and 1 unit of F2 cost rupees 2.5. This 2.5. And then the minimum daily requirement of vitamin A is 40 and B is 50 units. So this is 40 units and this is 50 units. So if we draw a table like this, then it will be easy to formulate the given problem very easily. The same table is here again. So let us take, let X and Y represent the number of units of food F1 and F2 respectively. So we have taken X as the number of units of food F1 and Y as the number of units of food F2. So the objective function is we have to minimize the cost. Now 1 unit of F1 is rupees 5 and 1 unit of F2 is rupees 2.5. So the objective function is given by it is minimize z is equal to 5x plus 2.5y subject to the constraints And now we have the constraint regarding the vitamins. The minimum daily requirement for vitamin A is 40 units and minimum daily requirement of vitamin B is 50 units. We have the food F1 has 2 units of vitamin A and food F2 has 4 units of vitamin A. So subject to the constraints, we have taken F1 as X and F2 as Y. So 2X plus 4Y greater than or equal to 40. Now let us simplify this. We have X plus 2Y greater than or equal to 20. So this is the constraint with respect to vitamin A. And then we have the constraint with respect to vitamin B. The food F1 has 3 units of vitamin B and F2 has 2 units of vitamin B. So the next constraint is 3x plus 2y. It should be greater than or equal to 50 because the minimum daily requirement of vitamin B is 50 units. So the next constraint is 3x plus 2y greater than or equal to 50. And then we have the non-negative constraints, x greater than or equal to 0 and y greater than or equal to 0. So this is the mathematical formulation of the given linear programming problem. Here this is also a diet problem. Now moving on to the next question. A brick manufacturer has 2 depots A and B with stocks of 30,000 and 20,000 bricks respectively. He receives orders from 3 builders P, Q and R for 15,000, 20,000 and 15,000 bricks respectively. The cost in rupees of transporting 1,000 bricks to the builders from the depots are given below. So the cost of transporting 1,000 bricks from depot A, then to builder P, it is 40 rupees. Then from depot A, then to builder Q, it is 20 rupees. Next from depot A to builder R is rupees 30. Then from depot B to builder P is 20 rupees. From depot B to builder Q is 60 rupees. And from depot B to builder R, it is 40 rupees. Now we have the question. How should the manufacturer fulfill the orders so as to keep the cost of transportation minimum? Formulate the above problem as a linear programming problem. So here we have a brick manufacturer who has 2 depots A and B with stocks 30,000 and 20,000 bricks respectively, and he received orders from 3 builders P, Q and R, and the cost of transporting from each of the depots to each of the builders is given in this table. Now we need to formulate this as a linear programming problem where our objective is to keep the cost of transportation minimum. So this is a transportation problem, which is the third type. So the sentence which is given in the question is written here. Now let us take, let 1 unit is equal to 1000 bricks and let x units of bricks be transported from depot A to builder P and y units of bricks be transported from depot A to builder Q. So let us draw the depots here and the builders here. So here we have depot A, this is depot A and this is depot B. And then here we have the builders P, Q and R. And now we have taken 1 unit is equal to 1000 bricks. So it means the capacity of depot A will be 30 units because we have taken 1 unit as 1000 bricks. The capacity of depot A is 30 units and the builders P, Q and R, they require 15,000, 20,000 and 15,000 bricks respectively. We have taken 1 unit as 1000 bricks. So P requires 15 units of bricks, Q requires 20 units and R requires 15 units. Now let us consider, as of now let us consider depot A and builders P, Q and R. Now we have taken, let X units be transported from depot A to builder P. So X units will be transported from depot A to builder P. And we have taken let Y units be transported from depot A to builder Q. So let Y units be transported from depot A to builder Q. And now after depot A has transported X units to P and Y units to Q, depot A is left with 30 minus X minus Y units, which can be transported to builder R. So here 30 minus X minus Y units will be transported to builder R. And now let us consider these three builders and depot B. Now here we can see that the requirement for builder P is 15 units of bricks. After getting X units from depot A, the remaining 15 minus X units P has to get from depot B. So depot B will provide 15 minus X units. And now here builder Q is getting Y units of bricks from depot A. The requirement is 20. It means Q has to get 20 minus Y units from depot B. So depot B will provide 20 minus Y units of bricks. And then moving on to builder R. Builder R is getting 30 minus X minus Y units from depot A. Then the remaining 15 minus of 30 minus X minus Y, he or she will receive from depot B. So here we have 15 minus of 30 minus X minus Y. So it is X plus Y minus 15. So this is how the transportation of bricks occurs. Now the constraints are nothing but each of these should be greater than or equal to 0. So those will be the constraints. So first let us write the constraints. We will write the mathematical formulation separately here. So this is just rough. So the constraints are x greater than or equal to 0, then y greater than or equal to 0, and then the next constraint is 30 minus x minus y greater than or equal to 0. Which means x plus y less than or equal to 30. And then we have the remaining constraints 15 minus x greater than or equal to 0, 20 minus y greater than or equal to 0, and x plus y minus 15 greater than or equal to 0. So 15 minus x greater than or equal to 0, it means x less than or equal to 15. Then 20 minus y greater than or equal to 0, it means y less than or equal to 20. Then x plus y minus 15 greater than or equal to 0. It means x plus y greater than or equal to 15. So these are the constraints. And now we have to find the objective function. Now we are given the cost of transporting 1000 bricks from each of the depots to each of the builders in this table. So the cost of transporting 1000 bricks from A to builder P, it is 40 rupees. So this is rupees 40. Then the cost of transporting 1000 bricks from depot A to builder Q is 20 rupees. So this is 20. Then the cost of transporting 1000 bricks from depot A to builder R is rupees 30. So this is 30. And then the cost of transporting 1000 bricks from depot B to builder Q is 20. So this is rupees 20. Then the cost of transporting 1000 bricks from depot B to builder Q is 60. So this is rupees 60. And then the cost of transporting 1000 bricks from depot B to builder R, it is 40. So here we have rupees 40. So here the cost of transportation is rupees 40. Now the objective function is we have to minimize the total transportation cost. Here we can see that X units of bricks are transported from depot A to builder P. So the total cost of transporting bricks from depot A to builder P will be 40 into X. So we have to minimize Z is equal to 40X plus, and here the cost of transporting 1000 bricks from depot A to builder Q is rupees 20. So the cost of transporting Y units of bricks will be 20 into Y. So plus 20 into Y. Then plus, here the cost of transportation will be 30 into 30 minus X minus Y. Plus 30 into 30 minus X minus Y. Then the cost of transporting from depot B to builder P, it will be 20 into 15 minus X. Let me write this here. 20 into 15 minus X plus the cost of transporting from depot B to builder Q will be 60 into 20 minus Y. 60 into 20 minus Y plus 40 into X plus Y minus 15. So we have to minimize this total cost. So if we simplify this, we will get the objective function. So let us simplify this. So this is equal to 40x plus 20y plus 900 minus 30x minus 30y, then plus 300 minus 20x, then plus 1200 minus 60y, then plus 40x plus 40y minus 600. So if we simplify this, we will get the objective function. Now let us write the mathematical formulation here. So the objective function is minimize Z is equal to, so here we have 40x minus 30x is, it is 10x minus 20x minus 10x plus 40x, it is plus 30x. 30x, and then here we have 20y minus 30y is minus 10y, then minus 60y is minus 70y, plus 40y is minus 30y. 30x minus 30y, and then we have 900 plus 1200, then minus 600, so it is plus 1800. So this is the objective function. Minimize Z is equal to 30x minus 30y plus 1800, subject to the constraints. Now these are the constraints. So we have the constraints here. Usually we write the non-negative constraints at the last. So let us write the remaining constraints first. X plus y less than or equal to 30, x less than or equal to 15, y less than or equal to 20, and x plus y greater than or equal to 15. Then we have the non-negative constraints. X greater than or equal to 0 and y greater than or equal to 0. So this is the mathematical formulation of this given problem. Now these things can be done in the rough. It is important to draw this diagram. So this is how we have to go about in mathematical formulation of a transportation problem. Moving on to the next question. A cooperative society of farmers has 50 hectares of land to grow two crops X and Y. The profit from crops X and Y per hectare are estimated as rupees 10,500 and rupees 9,000 respectively. Then, to control weeds, a liquor herbicide has to be used for crops X and Y at the rate of 20 liters and 10 liters per hectare. Further, no more than 800 liters of herbicide should be used in order to protect fish and wildlife using a pond which collects drainage from this land. How much land should be allocated to each crop so as to maximize the total profit of the society? Formulate the above problem as a linear programming problem. So here it is given a cooperative society has got 50 hectares of land to grow two crops X and Y. The profit from X is rupees 10,500 and from Y is rupees 9,000 per hectare. And then to control weeds, a herbicide is being used at the rate of 20 liters for X and 10 liters for Y. And it is also given no more than 800 liters of herbicide should be used. Now we need to find how much land should be allocated to each crop so as to maximize the total profit of the society. So here we need to find the land that must be allocated to maximize the total profit. So let us take, let X and Y represent the number of hectares of land allocated for crop X and crop Y respectively. So if we have taken X as the number of hectares allocated for crop X and Y as number of hectares allocated for crop Y, then the objective function is we have to maximize the profit from crop X and crop Y. So we have to maximize 10,500 X plus 9,000 Y. Then the objective function is given by maximize Z is equal to 10,500 X plus 9,000 Y. Now what are the constraints? Subject to the constraints, here the maximum area of land available is only 50 hectares. Now we have taken X as number of hectares of land allocated for crop X and Y as number of hectares allocated for crop Y. The total land available is only 50 hectares. So the first constraint is X plus Y less than or equal to 50. And then the second constraint is, it is given a liquid herbicide can be used for X and Y at the rate of 20 liters and 10 liters per hectare, and the maximum should be 800 liters of herbicide. So the next constraint is 20X plus 10Y. This should be less than or equal to 800. And then we have the non-negative constraints, X greater than or equal to 0 and Y greater than or equal to 0. Now this let us simplify. This implies 2X plus Y less than or equal to 80. So this is the mathematical formulation of the given linear programming problem. Now coming to the next question. A company has two grades of inspectors 1 and 2 to undertake quality control inspection. At least 1500 pieces must be inspected in an 8-hour day. Grade 1 inspector can check 20 pieces in an hour with an accuracy of 96%. Grade 2 inspector checks 14 pieces an hour with an accuracy of 92%. Wages of grade 1 inspector are rupees 5 per hour, while those of grade 2 inspector are rupees 4 per hour. Any error made by inspector costs rupees 3 to the company. If there are in all 10 grade 1 inspectors and 15 grade 2 inspectors in the company, find the optimal assignment of inspectors that minimize the daily inspection cost. Formulate the above problem as a linear programming problem. So here we can see that there are two grades of inspectors 1 and 2 who undertake quality control inspection, and a total of 1500, at least 1500 pieces must be inspected in an 8-hour day. And it is given grade 1 inspector can check 20 pieces and the accuracy is 96%. Grade 2 inspector checks 14 pieces in 1 hour and the accuracy is 92%. The wages for grade 1 inspector is rupees 5 per hour and for grade 2 inspector it is rupees 4 per hour. Then any error which is made by the inspector costs rupees 3 to the company. And there are in all 10 grade 1 inspectors and 15 grade 2 inspectors. We need to find the optimal assignment of inspectors that will minimize the daily inspection cost. So here the objective is to find an optimal assignment of inspectors so that the daily inspection cost is reduced. So this is an assignment problem. So we have to find how many number of inspectors should be assigned so that the total cost is minimized. Now let us take let x and y represent the number of inspectors of grade 1 and grade 2 respectively. So here if we draw a table, it will be easy for us to formulate the given problem. Now maximum number of inspectors, we have 10 grade 1 inspectors and 15 grade 2 inspectors. So there are 10 grade 1 inspectors and 15 grade 2 inspectors. And then the rate of checking per hour of grade 1 inspector is 20. So grade 1 inspector can check 20 pieces per hour, whereas grade 2 inspector can check 14 pieces per hour. And then next we have inaccuracy in checking. Here it is given grade 1 inspector can check with an accuracy of 96%. So the inaccuracy in checking will be 1 minus 0.96, which is 0.04. And grade 2 inspector's accuracy is 92%. So inaccuracy of grade 2 inspector will be 1 minus 0.92. It is 0.08. And here it is given any error made by the inspector costs rupees 3 to the company. So cost of inaccuracy of grade 1 inspector is rupees 3 and for grade 2 inspector is also rupees 3. Next we have the wage rate per hour. Here we have wages of grade 1 inspector is rupees 5 per hour and for grade 2 inspector it is rupees 4 per hour. So we have drawn the table. Now we have to minimize the total cost, daily inspection cost. First let us find the hourly cost for grade 1 and grade 2 inspector. So hourly cost for grade 1 inspector it is equal to 5 plus the wage rate is 5 and then we have the cost of inaccuracy. So it will be 3 into the inaccuracy in checking is given by 0.04 and the rate of checking in 1 hour is 20 pieces into 20. So this is the hourly cost for grade 1 inspector. Now this is the wage and this is the cost of inaccuracy of grade 1 inspector. It is 3 into inaccuracy of grade 1 inspector into the number of pieces which grade 1 inspector checks in 1 hour. So it is 3 into 0.04 into 20. So it is 5 plus 2.4 which is rupees 7.4. And then we have the grade 2 inspector. For grade 2 inspector it is equal to the wages is 4 plus the cost of inaccuracy is 3 and the inaccuracy in checking is 0.08. Then the number of pieces checked in 1 hour is 14. Now this is equal to 4 plus 3.36. So which is 7.36. So the hourly cost for grade 1 inspector is 7.4 rupees and for grade 2 inspector is 7.36 rupees. Now we can write the objective function. So the objective function is minimize z is equal to, here the hourly cost is 7.4. Now there is an 8-hour day, so the total cost will be 8 into 7.4 x plus 8 into 7.36 y. Since we have taken x and y as the number of grade 1 and grade 2 inspectors respectively, so we have to minimize z is equal to the hourly cost of grade 1 inspector into the number of grade 1 inspectors into the total number of hours in one day, plus similarly for grade 2 inspector. So this is equal to 59.2x plus 58.88y. Now we have the constraints. The constraints are easy. Subject to the constraints, here we have the maximum number of grade 1 inspectors is 10 and grade 2 inspectors it is 15. So we have x less than or equal to 10, then y less than or equal to 15, and then we have the next constraint, at least 1500 pieces have to be inspected. So we have (20 into 8x plus 14 into 8y. This is greater than or equal to 1500. So here we have the rate of checking per hour of a grade 1 inspector is 20. So in 1 hour grade 1 inspector can check 20 pieces. So in an 8-hour day grade 1 inspector can check 20 into 8 pieces. Similarly, in 1 hour grade 2 inspector can check 14 pieces. In an 8-hour day grade 2 inspector can check 14 into 8 pieces. So the minimum number of pieces that must be inspected is 1500. So we have 20 into 8x plus 14 into 8y greater than or equal to 1500. So this implies 160x plus 112y should be greater than or equal to 1500. And finally we have the non-negative constraints, x greater than or equal to 0 and y greater than or equal to 0. So these are the constraints and this is the objective function. So this is an assignment problem where we have to assign grade 1 and grade 2 inspectors in such a way that the daily inspection cost is minimum. This is the mathematical formulation of this assignment problem. I hope this video was useful for you. In my next video, I'll start with solving linear programming problem using graphical method, that is corner point method. Thank you for watching.